Hello, good morning. Welcome to One Concept Per Day portal. This concept today, which we are discussing today, is about conservation of momentum and its application in nuclear physics, radioactive decay, and collisions. Okay, so with this, as you know, this paper has been taken from May 2005 HL portions, TZ2 time zone. Okay, so these papers are really good enough to discuss all the concepts or all the different types of problems. Okay, from one concept. That's why I've been choosing only problems from the previous papers. Okay, and if you want to find this question paper completely, you can just refer to my WhatsApp group. The WhatsApp group is available at this link: https://ibphysics with RAW. In fact, this IB physics with RAW, RAO, okay, is seen to be common in all my websites. My social media handles is the same link is being used everywhere. So the moment you go and type in Google, you will be able to find out only links with this particular place. Okay, now let us begin without wasting our time. The first question is about collisions. Define linear momentum and impulse. What is linear momentum? Linear momentum is nothing but mass multiplied by velocity. Okay, and impulse is nothing but force multiplied by time. So here it is for 2 marks. So you need to mention the formulae, or maybe you can mention as mass into velocity, product of mass into velocity. You can mention like this also. But you need to explain what is M stand for, what is V stand for, F stands for, T stands for. Okay. Next, let us move on to the next one. Say the law of conservation of momentum. So what is the law of conservation of momentum? Don't just say momentum before collision equal to momentum after collision. That is an incorrect statement. So you should say in the absence of external forces, the momentum is constant or conserved. Don't even mention constant, it is incorrect. It is conserved. Right? Conserved. Or still, if you want to write, and in terms of collision, in the absence of external forces, in a collision, the momentum before collision is equal to momentum after collision. You can mention like this also. Okay. Then next, using your definitions in A1, deduce that the linear momentum is constant for an object in equilibrium. Now, using the definitions there, what we have got, we have said that F external is equal to 0. What does it mean? Which means that delta P divided by delta T is equal to 0. What do you mean by delta P by delta T? Change in momentum by change in time taken. It is nothing but Newton's law. Though the net force is equal to 0, I can write delta P by delta T equal to 0, or you can write delta P is equal to 0, which means what is delta P? Final momentum minus initial momentum is equal to 0, which implies the final momentum is equal to initial momentum. But what is being asked? Linear momentum is constant for an object in equilibrium. In an equilibrium, so you see that wherever you take the final, wherever you take the initial momentum is not changing. Okay. So for example, if I take an object over here and then it collides with some other object, the initial momenta of these two objects could be, it could be m1 u1 here, and this could be m2 u2 over here. Let me assume that this object is at rest, which means what? U2 is equal to 0, and this object is in motion, which means what? U1 is in motion, right? U1 is a positive value over here. So the sum of the momenta would be m1 u1 plus m2 u2. What is m2 u2? It is 0. This should now be equal to, after collision, what happens then? Let us say the second object is now trying to move like this. Okay, let me write it down here. Second object, the round object, is now trying to move with a velocity v1, and the square object that I see is trying to move with a velocity v2 over here. Okay, that means both of them have some momentum, and the momentum they are in the same direction. So I can now say m1 v2. Since this is mass m1, this is v2, I will write this as m1 v2 plus this mass is m2 over here. I have said m2 over here plus m2 v1. Usually you have studied something like m1 v1 plus m2 v2. I have put this m1 v2 plus m2 v1 because I want to make sure that you understand how to write the velocities and how to write the momentum. That's why I have changed it over here. Okay, now let us move on to the next one. Okay, now a stationary radar nucleus undergoes alpha decay to form a nucleus of polonium, and the alpha particle has a kinetic energy of so much. Complete the nuclear reaction for this decay. So you need to complete the nuclear reaction. Now you see, what does it say? It says radon nucleus forms a polonium nucleus. Polonium nucleus, and there is an alpha particle emitted. Alpha particle. What is alpha particle given by? Alpha particle is 2He4. So let me write down here 2He4. What do you mean by 2He4? 2He4 is nothing but 2 protons and 2 neutrons. The total number of nucleons is 4 here and 2 protons over here. So therefore, I need to balance the reaction, like the way how you do it in chemistry. You need to balance it. So what do you do here? If this is 2 here, this should have been 84. If this is 220 over here, this can be 216 over here. So 216 plus 4 becomes 220. 84 plus 2 becomes 86. Okay, so this is done. Then calculate the kinetic energy in joules of the alpha particle. So you need to find out the energy in joules for the alpha particles. What is been given? The alpha particle of kinetic energy of 6.29 million electron volt. So this energy is given. So now let me write down 6.29 million electron volt. So what I need to do is convert it into joules. How do I convert? I need to write this as 6.29 into million. What is million? 10 power 6 multiplied with E. What is E? Electronic charge. It's 1.6 into 10 to the power of minus 19. If I do the whole process, then this can be represented as joules over here. E into V is nothing but you can express in joules. Okay. So therefore, I put this as joules. I replace this V with joules over here. Okay. And now what I do is, let me take my calculator to find out what is this value. Okay. Now 6.29. Let me show you the calculations also. 6.29 multiplied by 1.6 will give me 10.064. 10.064 into 10 to the power of, here you have 6, you have minus 19, it should be minus 13 joules. Okay, so this is what we have got. We have got the kinetic energy in joules. Okay. Next, what's the next thing? Reduce the speed of the alpha particle. Reduce the speed of the alpha particle is 1.74 into 10 power 7 meter per second. We need to find out what is the speed. How do you find the speed? We know that kinetic energy is given by half mv square. So therefore, what is this value? This value we have already got. How much is this value? This is 10.064 into 10 power minus 13, or maybe I can now write this as, you have 6 here, right? So I can put an approximation here, and I can now write this as 10.1 into 10 to the power of minus 13 joules. Now this should be equal to 1.01 into 10 to the power of minus 12 over here, because 3 significant figures. Okay, now this I can put it over here, 1.01 into 10 to the power of minus 12 over here. Now I need to find what's the mass of the alpha particle. Now what is an alpha particle? Alpha particle, as you see here, it is 2He4. What does it tell you? Which means mass of an alpha particle should have 2 mass of a proton plus 2 mass of a neutron. But we already know mass of a proton is nearly equal to mass of a neutron. I'll use this approximation, and I will now write m alpha equal to 2mp. Since mp is equal to n1, I'll write this as mp itself. 2mp, which should now be equal to 4 times mp over here. What's the mass of one proton? Mass of one proton is 4, and mp is nothing but 1.67 into 10 to the power of minus 27 kg. You can find this in the data booklet also. Now what I will do is, let me substitute these values and get the value of V. That's what we need to find, speed, right? So it should now be half multiplied by 4 multiplied by 1.67 into 10 to the power of minus 27 into velocity square is equal to 1.01 into 10 to the power of minus 12. Okay, so I'll get the value of V, which is V square. I'll push all this downwards. It should be 1.01 into 10 to the power of minus 12 divided by, so this 2 goes upwards. I'll multiply this by 2, and then this 4, or whatever term you have, it comes downwards. 4 into 1.67 into 10 to the power of minus 27. Okay, now let us calculate this. The calculator is here. I have 1.01 into 2 is equal to so much, divided by 4 is equal to so much, and this is divided by 1.67. When I do this, I get 0.3023, something I get. I'll try this as 0.302 multiplied by 10 to the power of, here you have minus 12 and here minus 27, comes upwards, it becomes plus 27. Plus 27. So this should be 0.302 multiplied by 10 to the power of 7 minus 2 is 5, 2 minus 1 is 1, 15 over here. So I need to get the value of V. V value will now be equal to square root of 0.302 multiplied by 10 power 15. Now what I'll do is I'll just write this for the sake of convenience. I'll write this as 3.02 into 10 to the power of 14. I hope now you understood why I wrote like this. Because 10 power 14 is nothing but square root of this one is 10 power 7. I just need to find out this value. Okay. We will not rely more on our calculators. We will do all those things manually, and then if possible, then we'll go for the calculators. Then I'll write 3.02. I'll take the square root of this. I get 1.73. 1.73 multiplied by 10 power 7. What is this V? V is nothing but meter per second. Right? It's meter per second. Okay, we have got the value of the velocity. Value of the velocity is equal to 7. Next. The decay shows the alpha particle and the polonium nucleus. Immediately after decay, the direction of the velocity of the alpha particle is indicated. Alpha particle direction is indicated. Then on the diagram below, draw an arrow to show that the initial direction of motion of the polonium nucleus immediately after the decay. He is asking you how does the polonium nucleus work? Okay, which is the direction of the polonium nucleus. So according to conservation of momentum, if this particle is going like this, this particle should go oppositely directed. Okay. Now, how do I know that? I'm just putting across a fact over here, right? So now what we do is, let us imagine like this. What is the momentum of the radon nucleus? Okay, initially these were together to give rise to a radon nucleus, right? Radon nucleus. What is the momentum of this? The velocity of this was equal to 0. So therefore, the momentum of this is equal to m into v, which was equal to 0. Initial momentum. What is the final momentum? Final momentum is nothing but this alpha particle will have m alpha v alpha. Polonium nucleus will have m polonium v polonium. Okay. I do not know what is the direction of this. Okay. I just told you directly like this. Let us verify whether my claim is correct or not. So this is a vector. This is also a vector. Okay. So therefore, if this is equal to 0, what do we get here? I get m polonium v polonium is equal to minus m alpha v alpha. Okay. So in other words, I can now write v polonium, vector v polonium is equal to minus m alpha divided by m polonium multiplied by v alpha. Now you see, the m alpha by m polonium is nothing but a scalar. It is some number, some fraction, something you will get over here. Okay. If you want, you can determine this also. Okay. But the direction of this is a negative side. If v alpha vector is like this, v polonium vector would be directed like this. Don't worry about the magnitude over here. Magnitude will definitely be smaller. If this arrow is so much, I should be writing this arrow only of this much. Okay, it should not be this much length. It should be smaller over here. I hope you understood this concept. So what did we do? We applied conservation of momentum to this particular reaction. Okay, next. Let us move on to the next one. Determine the speed of the polonium immediately after the nucleus, after the decay. Okay, so that's what we have got. Okay, so therefore, what we need to do, we will use this equation. We will use V polonium is equal to minus of m alpha divided by m polonium into V alpha. All these are vector quantities. It asks you about the speed, which means what? I can neglect the direction, which means I can even neglect this negative also. I can put this positive. Now let us write down what is the mass of alpha particle. 4 times mass of the protons. That's the mass of the alpha particle. What is the mass of polonium? What is polonium here? We already determined the mass number of polonium. How much was it? See here, polonium 216 nucleons are there, right? So therefore, if this is 4, this is 216. Don't worry about the proton number. Mass does not depend upon the proton number. Therefore, this is 216 times m over here. MP if you want to write. So this 2 goes away because I said mass of proton and mass of neutron are equal, so I put it like this into V alpha. Now what will I do with this? This should now be equal to 4 by 216 multiplied by what's the value of V alpha? We have just now found out V alpha. V alpha value was 1.73 into 10 power 7. Previously we have seen, which should be 1.73 into 10 to the power of plus 7. Which should now be, let me use my calculator now, which will give me 4 divided by 216 okay, multiplied by 1.73. I get this answer as 0.032. 0.032 into 10 to the power of 7 meters per second. Let us write it in three significant figures. I need a third point also here. 3201. Okay, 3201. 321. It should be 3.2 into 10 to the power of 1, 2, 1, 1, 2, 1, 2, 10 to the power of 5 meters. This should be my velocity of polonium. It's really faster. Okay, so this is going to be part of the answer. Let me check this in my marking scheme. So we have got the correct answer. Right. Okay. Next. In the decay of another radon nucleus, the nucleus is moving faster, moving before the decay without any further calculation, suggests the effect, if any, on its initial speed of the part shown in C1. So what does it say? In the decay of another radon nucleus, the nucleus is moving before the decay. In our case, what happens? The radon was at rest, and then this gave rise to radon was at rest, and this gave rise to a polonium nucleus. Okay, let me write the hat over here. This is for your polonium nucleus plus an alpha particle. And then I suggested that the alpha particle is going like this, polonium nucleus is going like this. Okay. But here what's happening is, this radon nucleus, which is not at rest, it is already moving as a velocity. Okay. As a result of it, now what will happen? Initial speed of the path shown over here. What will be happening to this one here? So this is the question. So towards it, what you can say? You can first say, see, we do not know. Okay, what will happen over here? We can just say first one is that maybe the directions of these two may not be opposite. Okay, because it is moving like this, and suddenly if this goes in this direction, okay, there is a possibility that the polonium nucleus and the helium nucleus are not in opposite direction. You can say helium and polonium nucleus may not be in opposite direction. May not be in opposite direction. We can mention this also. Then what else can we say? We can say that second one. We can say that because it's for 2 points, right? So we can say maybe polonium nucleus may be at rest after D. This can also be possible because he says without any further calculation, it's a speculation. Okay, what else can happen? Okay, that's what has been asked. Next, let us move on to the next. The half-life of the decay of radon is 3.8 days and radon 220 is 55 seconds. Suggest three ways in which the nucleus of radon 222 differ from that of radon 220. Now it is like you take a pinch of radon with you, 220 and 222 with you, both in two hands, and you find out what is this. Okay. So radon 220 leaves in your hand only for 55 seconds. You take 10 grams of it within 55. After 55 seconds, it becomes 5 grams, right? Okay, but this one you have to wait for 222, 3.8 days. So therefore, what can you say? This is unstable. The moment you look into it, you can say the radon 220 is unstable as compared to radon 222. See, what is being asked is what is your observation? Okay, what is your observation to say that these two nuclei are different? So towards it is the first thing that you can say. The second one, what's the second one you can say? You can say, see, radon 222. Now let me go back to the composition of radon 222 and radon 220. Now what is the composition here? Radon 222, what was the proton number for radon? Proton and neutron number. Let us find out. 86 radon. Okay, so I will go back to this. I will type this as this was 86. This should also be 86. Okay. When the proton number does not change, the element will not change. It will remain the same. So because it's an isotope here, this is an isotope of this one. So as a result of it, it will not change. Now you have 86 over here, this 222. 86 here, 222, 220 over here. What's happening in radon then? You can say that radon 220 has less number of neutrons. Okay, proton numbers are one and the same, so less numbers of neutrons. which means what? Now what does it tell you? It tells you that if it has less number of neutrons, I can now represent this nucleus to be this much big, and this nucleus maybe this much big. So can you say now? You can say that the diameter of radon 220 is less than diameter of radon 222. Okay, all these are factual observations. The moment you look into it, you will get it. But the only thing is, this tests you about the skill of how do you observe, how much do you observe. Okay, it's a very important skill that you know. It's a research skill you are looking at. Okay, now let us move on to the next. Define half-life. How do you define half-life? What is half-life first of all? Half-life is nothing but the time taken for the activity to reduce it to half. You can write like this, or you can also say time taken for the number of nuclei to reduce it to half. You can write like this. Okay, both are same. Next, because what happens over here is that if you have a number of nuclei, let us say for example you have 1000 nuclei, after one half-life, what will happen? This will become 500 nuclei, and next half-life, this initial nuclei will become 250 nuclei. This is what we call as half-life. The time taken for it to reduce it from 1000 nuclei to 500 nuclei will be, let us say, 10 seconds, for example. I'm just saying an example. It's not it depends upon the nuclei that you are using over here. 10 seconds in this case. So here also it will be the same 10 seconds. Next also it will be only 10 seconds. Okay, let us move on to the next. State the expression that relates the activity AT of time t of a sample of radioactive material to its initial activity A0 at time t equal to 0 and to the constant lambda. Use this expression to derive the relationship between decay constant lambda and T. We need to derive an expression for lambda and T. Okay. Now we know that AT is given by A0 e to the power of minus lambda T. What is this now? This is an expression that tells you how does the activity changes with respect to time. Okay. Now what does it say? Now we know that whenever AT becomes, when does AT becomes A0 by 2? Okay. The population becomes half the population. Then the time taken for it to become like this is nothing but T divided by 2, or T half. Not T divided by 2. So let us say half-life. Half-life, I'll just write it as capital T. T half is half-life, and it is T here. So what we will do is we will substitute over here. We write A0 by 2 is equal to A0 e to the power of minus lambda into capital T. Okay. So this A0 goes away. We have half is equal to e to the power of minus lambda. Now take logarithm on both the sides, which will give me ln of half is equal to ln of e to the power of minus lambda into t. Now this I can take it that side. I will write this as minus lambda into t. Ln e to the base e. We know ln e to the base e tends to 1. So therefore, I have ln half of. What is ln of half value? So this can be written as ln 1 minus ln 2, ln a minus ln b is equal to minus lambda t. Ln 1 is 0, ln 2 is 0.693. 0.693 is equal to minus lambda t. Negative sign goes away. So you can say lambda t is equal to 0.69. Either you can stop here, or you can just say lambda equal to 0.693 divided by 2. Both are. Okay, this is a relationship connecting these quantities. Then next, radon 222 emits alpha particles. The activity of radon gas in a sample of 1 cubic meter of air is 4.3 becquerel. This is what A222. Given 1 meter cube of air contains 2.6 into 10 power 25 molecules. This is your number of molecules in air. Determine the ratio. What is given? Denominator is given. You need to find numerator and then substitute this for this one and then find out the ratio over here. So how do we find? Now we know that A is equal to A0 e to the power of minus lambda n over here. Okay, and we also know lambda t. We also know that the activity can be written as lambda into n over here. A equal to lambda into n. Right? So thus what we can do is we need to find out the value of n. So value of n is equal to a divided by lambda, which should be, what is a? A is already given to you, 4.6 becquerels. 4.6 divided by, what is lambda here? Lambda is the value of lambda given. Lambda is not given, but you know this lambda into t. Okay? You know this value of lambda into t. But if you know the value of t, then you can easily find out. What's the value of t? Which t here? T is nothing but the half-life. Half-life of whom? Half-life of radon. Okay, let me go back and see where do I get half-life of radon here. It's somewhere given over here. I think it was given as 3.8. Right? So I will take this value. I will now write, to calculate this, I need the value of lambda. So towards it, lambda into t is equal to 0.693. Lambda should be equal to 0.693 divided by t, which should be 0.693 divided by 3.8 days. Okay, so which I will once again write this as equal to 0.693 divided by 3.8 into 1 day has 24 hours, and each hour has 3600 seconds. 3600 seconds. When I do this calculation, I get this as 0. Okay, let me do the calculation here. So this would be 0.693 divided by 3.8 is equal to so much, divided by 24 is equal to so much, divided by 36,000, sorry, not 3,600 will be 2.11 into 10 to the power minus 6. 2.1 into 10 to the power of minus 6. This is your lambda. Now what I will do is, I can substitute it over here. Then I get the value of n. What is this n here? Radon. N radon I can. N radon is equal to 4.6 divided by 2.1 into 10 power minus 6, which would be, it's a big problem, 4.6 2.1 is 2.19 into 10 to the power of plus 6, right? This is what we get over here. And then now what I will do is, what is this now? N radon. I'll take this value, substitute it over here. This would be 2.16 into 10 to the power of 6 divided by 2.6 into the power of 25. 2.6 into 10 to the power 25. Now which ratio of this will now be equal to, it should now be equal to, it's just 2.19, I'm sorry. Here, 2.19, see here. So this will be 2.19 divided by 2.6. And I get this 0.85, you get 0.8423 here, 0.8. 0.84 into 10 to the power of 6 minus 25 is minus 9. So thus, this ratio would be equal to 8.4 into 10 to the power of minus 20. No unit. Okay. So with this, I think with this we have come to an end to this particular problem. Thank you.